Welcome to Mastering Solutions. In this problem, they want us to find out first what is the magnitude of John's displacement from where he started to where he ended up. And then we have to figure out if Jane were to start at the same place but walk in a straight line, what speed she could walk to get to the same place right whenever John does. So let's start off first by drawing a little compass. We have north, south, east, and west, so we get our directions correctly. And now let's draw a picture of what they say happened. So they say that John walks 1 kilometer north, so 1 kilometer north, and then he turns right and walks 1 kilometer east, 1 kilometer east, and then his speed was 1.5, so his velocity was 1.5 meters per second. And then what is the magnitude of his displacement, which is a straight line from where he started to where he ends, which we just created a triangle, obviously. So for part A, to find the displacement, we can use Pythagorean's theorem to solve for this. So c squared is equal to a squared plus b squared. If we isolate c by taking the square root of both sides, that gives us c is equal to the square root of a squared plus the square root of b squared. So now c is going to be the square root of 1 squared plus 1 squared, which is simplified to the square root of 2. Now we can get an approximate answer by taking the square root of 2 and then hitting the approximate button right here. So 1.414. So for part A, his displacement is 1.414 kilometers. And now for Jane, to figure out the speed that she needs to walk to get there at the same time, let's scroll up to get a little bit more space. For part B, we're going to be using the velocity formula. So essentially what they're saying is if Jane were to walk along that displacement line, if we redraw our triangle here, if Jane were to walk from here to here, but John is going his path that way, how fast does she have to walk to get there in the same amount of time John does? So to do that, let's make a list really quickly. So we'll say Jane, her distance that she has to walk, as we just found out, is 1.414 kilometers. And the velocity is what we're trying to find, and we don't know how long she has to do it in. Now for John, he goes a total distance of 1 north and then 1 east. So his total distance was 2 kilometers. And let's put these into meters. So that is, of course, 2,000 meters. And this is 1.414 meters. Now his velocity, they told us, is 1.5 meters per second, as we wrote above, and we don't know what his time is. So we need to figure out how long it took John so we know how long Jane has to do it. So velocity is equal to a change in a distance over a change in time. And so we want to solve for time, so we'll multiply both sides of the equation by t. So delta x is equal to v times delta t. Then we isolate that by moving v over. So now we have delta t isolated is equal to the change in distance divided by the velocity, which makes sense because we'll have meters up here and divided by meters per second, so the meters will cancel and we'll be left with seconds. So now when we plug this in, we know he went 2,000 meters divided by 1.5 meters per second. 2,000 divided by 1.5 meters per second. So he did it in a time of 1,333.33 seconds. So now that's the time that Jane has to do it in here. So now we can use the same velocity equation. Velocity is a change in distance over a change in time. So v is delta x over delta t. We know the distance that she has to walk because we found that for the first part for John, which we said is 1,414 meters. And we need to find the velocity by dividing by the time that John did it in, which is 1333.33 seconds. So now we have 1414 divided by 1333.33 seconds, which gives us 1.06. So her velocity that she has to walk is she has to walk at 1.06 meters per second to get there at the same time John does.